All right, today we're going to dive into one of the coolest stories in all of tech, how we actually taught computers to see. It all happened in this incredible 4-year sprint, where 4 revolutionary neural networks didn't just learn to recognize pictures. They literally built the foundation for the AI that's in your phone, in your car, everywhere. So let's get into it.
You know, to really get a handle on the whole AI explosion of the last decade, you have to ask this one simple question. What was the Big Bang moment? What was that single spark that just lit the fuse for this whole revolution? Well, the answer, it turns out, lies in this super intense competition to solve one of our oldest challenges, vision.
Before we could even dream of self-driving cars or an AI that could describe a photo to you, we had to solve a much bigger problem. We needed to give computers a massive, like a truly comprehensive education in what the world actually looks like. And this was the great AI challenge that set the stage for everything that came after.
So, the classroom for this big AI education project was something called ImageNet. The best way to think about it is like the ultimate visual encyclopedia for a machine. It was just this colossal data set of images, every single one of them meticulously labeled by humans, and it was designed for one purpose, to train and test an AI's ability to see and understand.
And when I say colossal, I am not kidding. The full ImageNet dataset has over 14 million images. That scale is it's absolutely essential. I mean, for an AI to really learn what a cat is, it can't just see 1 or 2, it needs to see thousands of them. Different breeds, different angles, in all kinds of situations.
But it wasn't just about the sheer number of pictures. It was the complexity. The dataset had over 21,000 different categories. So the AI didn't just have to tell a cat from a dog. No, it had to tell a Siberian husky from an Alaskan Malamute. This was a brutally difficult test.
And to really spur innovation, this dataset became the foundation for a competition, the ImageNet Large-Scale Visual Recognition Challenge. So every year, the brightest minds from all the top universities and tech companies would get together to see whose AI could actually conquer this thing. You can basically think of it as the Formula One of computer vision.
And then, in 2012, something happened that nobody saw coming. A new contender showed up, and it didn't just win, it completely changed the game, forever. Its name was AlexNet. And this was the Big Bang we were looking for. Now, you have to look at this chart to really appreciate the scale of this win. The competition measures something called a top 5 error rate. Basically, did the right answer show up in the AI's top 5 guesses? Before 2012, the very best models were sitting at an error rate of around 26%. Then AlexNet comes along with 15.3%. I mean, this wasn't an improvement, it was a quantum leap. It just stunned the entire field. So what was the secret sauce? Well, the thing is, AlexNet's creators, they bet the farm on one huge idea, that a really big, really deep neural network trained on powerful gaming GPUs was the answer. They proved that instead of trying to handcraft features for the AI, you could just let a giant model learn everything directly from the data. And they were so right. This was the moment deep learning truly arrived on the scene. Okay, so AlexNet's success basically fired the starting pistol on an arms race. By 2014, everyone was building deep neural networks, but a really fascinating debate popped up. To get better, should you just build your networks bigger and deeper, or could you build them smarter? This led to this amazing showdown between 2 totally different philosophies.
So on one side, you had VGGNet, coming out of the University of Oxford. Their philosophy was super simple. Depth is all you need. They used this very clean, very uniform design, just stacking layer after layer of these small filters. And then on the other side, you had GoogleNet. It was way more intricate, using this clever little building block they called an inception module that let it be both incredibly deep and computationally efficient.
And this table just lays it all out. Look at the number of parameters. Those are the little knobs inside the model that it has to learn. VGGNet was this absolute heavyweight, with around 138 million of them. GoogleNet, with its super efficient design, got slightly better results with only about 7 million. It was a total battle of brute force versus like a finely tuned Swiss Army knife. So how in the world did GoogleNet pull this off? Well, one of its genius moves was this thing called the 1-by-1 bottleneck convolution. Before doing a big expensive calculation, it would use this tiny, super cheap operation to kind of squeeze the data down first, just like a bottleneck in a pipe. And as you can see, this one simple trick slashed the number of computations by a factor of 3.6. It was just this brilliant piece of engineering that's still used all over the place today. So both VGGNet and GoogleNet proved that going deeper was definitely the right move. But
they hit a wall, and it was a really strange, really frustrating wall. So let's jump to the 2015 winner, ResNet, and see how it solved this final puzzle and pushed AI beyond what a human could do.
So here was the crazy problem. Everyone just assumed that deeper networks should always be better, right? But in the real world, once you got past a certain number of layers, the performance would actually start getting worse. It was like the network was so deep that the training signal, the information, was just fading away as it traveled all the way back through the layers. It was getting lost in transit.
The solution, which came from the ResNet team at Microsoft, was just pure genius. They introduced something called a skip connection. The best way to picture it is as an express lane for information. It lets the signal literally skip over a few layers and travel directly to a deeper point. And this meant the network only had to learn the changes, or the residual, at each step, which made it way, way easier to train ridiculously deep networks.
And the result of this? Wow. ResNet was able to go to an unheard of 152 layers deep, and it got a top 5 error rate of just 3.57%. That means in over 96% of the cases, the right answer was in its top 5 guesses. This was it. For the first time ever, an AI model had officially performed better than a human on this incredibly complex task. This was a monumental milestone.
So let's just step back for a second. In the span of just 4 years, we went from struggling to a massive breakthrough to this big debate over depth versus efficiency, and then, finally, to superhuman performance. This incredible race didn't just give us a winner each year. It built the very architects of the AI we use today.
Let's just run through that amazing journey one more time. 2012, AlexNet comes out of nowhere and proves the raw power of deep learning on GPUs. 2014, VGGNet and GoogleNet battle it out, exploring the best way to go deep. And then, 2015, ResNet solves that final piece of the puzzle, unlocking insane depth and blasting past the human benchmark.
And here's the most important takeaway. This isn't just a history lesson. These ideas are literally the Lego bricks that almost every single modern vision AI is built with. The next time you use facial recognition on your phone, or you see a self-driving car figuring out a busy street, you are watching the legacy of this race play out in real time. We are still using the simple, uniform kernels from VGGNet, the brilliant bottlenecks from GoogleNet, those game-changing skip connections from ResNet, and the fast activations that AlexNet made famous.
It's kind of wild to think about. This entire revolution was born from a competition to just classify static images. It really makes you wonder, right? The big AI races today are all about generating language, making video, even controlling robots. So what are the fundamental building blocks being invented right now that are going to define the AI of tomorrow? That's definitely something to think about. Thanks for tuning in.